Welcome to Chapter 2. Here we will study different types of polynomial functions, beginning with quadratics, then moving into polynomials of higher degrees, and then finally finishing off with some rational functions as well. So let's get started. Hop right into Chapter 2.1, dealing with quadratics. Now, by now you guys have all seen quadratic functions. All right, quadratics are a special type of polynomial. So let's start off with our definition of polynomials. Polynomials represent a special category of functions that are continuous for all real values of x. By definition, let n be a non-negative integer and let a sub n minus 1, a2, a sub 1, a sub 0 be real numbers with a sub n does not equal 0. The function given by f of x equals a sub n x to the nth plus a sub n minus 1 x to the n minus 1 plus plus a sub 2 x squared plus a sub 1x plus a sub 0 is called a polynomial function of x with degree n. Now, that's all very, very, very complicated, it seems, okay? But you guys have seen polynomials before. And so the best way to consider polynomials is to think about them in terms of their examples, right? Polynomials are classified by degree, which refers to the value of the largest power of x. All right, so key things with polynomials, all right? We're going to have different powers of polynomials, and the highest power tells us the degree. This is a polynomial of degree 4. Why is this a polynomial of degree 4? Well, our highest power of x is raised to the 4th power. Okay. G of x is equal to 5 minus 7x plus 2x squared. What is the degree of this polynomial? Well, the highest power of x is 2, therefore it is a polynomial of degree 2. H of x is equal to 8. This is also an example of a polynomial. Notice that this is also a constant function, and we actually have x raised to what power here? In this case, this would be degree 0. Technically, I could have an x raised to the 0 power. Remember that any non-zero number raised to the 0, okay, is going to be 1. And here we have k of x is equal to 5 minus 24x. This would be a polynomial of degree 1. This is an example of a linear polynomial. All right, so all of these are different types of polynomials. You guys have dealt with polynomials in the past. So let's take a look more at quadratics. So any polynomial function of degree 2 is called a quadratic function, and its graph is known as a parabola. Okay, here I have a function f of x is equal to x squared plus 6x plus 2. This is a quadratic because it has a degree of 2. G of x is equal to 2 times x plus 1 quantity squared minus 3. This is also a quadratic function. Again, if you were to multiply all this out, your highest power of x would be 2. H of x is equal to 9 plus 1/4 x squared. Again, another quadratic function. And k of x is equal to x minus 2 times x plus 1. These are all examples of quadratics. Notice if you were to FOIL or use the distributive property of multiplication here in k of x and multiply those two binomials together, you would indeed end up with a polynomial that has a degree of 2, right? X times x would give you x squared. The general form of a quadratic function is given by f of x equals a times x squared plus bx plus c. Okay, ax squared plus bx plus c, you guys have all seen that before. Here's another form that you might not be as familiar with, and this form is called standard form, or is often referred to as vertex form. And the reason we like vertex form is because it actually gives us the vertex of the quadratic. F of x is equal to a times the quantity x minus h squared plus k, where the ordered pair h comma a are the coordinates of the vertex of the parabola. All right, so having a quadratic written in vertex form or standard form can be very helpful because if we want to sketch a graph, we know exactly where the vertex of the parabola is going to be. A couple properties of our quadratic functions, right? Given a quadratic written either general form or standard form, here's our general form, ax squared plus bx plus c, or standard form, f of x equals a times x minus h quantity squared plus k. If a is greater than 0, that's our leading coefficient. That's going to be the constant term that ends up being in front of the x squared. All right, the parabola is going to open upward. Here we have an example. Parabola shape, this nice U, all right, and this parabola is indeed opening upward. And if that is the case, that means that the vertex with the ordered pair h comma k is going to be a minimum. All right, in this case, it looks like our vertex is located at 2 comma 1, and yes, it is a minimum value of our function. Now, every parabola also has an axis of symmetry. All right, the axis of symmetry for every parabola is going to be the vertical line x equals h, where h is the ordered pair, or is the x coordinate of the vertex. All right, if I were to draw the line x equals 2, that's a vertical line here with all my x values are 2, it would split this parabola right in half. Now, if we make a less than 0, that means that our parabola is going to open downward. And if you think about that in terms of transformations of functions that we studied in chapter 1.7, remember that if that constant multiple in front of the parent function is negative, that gives us a reflection over the x-axis. That's the exact same thing that is happening here. All right, our parabola will open downward, and this means that the vertex h comma k is going to be a maximum. Right, in this case, it looks like my maximum, my vertex, is at -3 comma 10. All right, and as we said before, the axis of symmetry is the vertical line x equals h, right, where h is the x coordinate of our vertex. All right, in this case, it would be x equals -3 would be our axis of symmetry. So now that we have our properties of quadratics down, let's see if we can't do a couple problems. Write the standard form of the equation of a parabola that has the indicated vertex and passes through the given point. All right, so if you want to write an equation of a parabola, you have to know where the vertex is located and you have to have a point. Well, just like any problem that requires a standard form, start off by writing down that equation. Standard form for the equation of a parabola is f of x equals a times x minus h squared plus k. We can begin by plugging in the values of our vertex. We know that this is the ordered pair h comma k. I'm going to plug in 2 for h and 3 for k. That gives me f of x is equal to a times the quantity x minus 2 squared plus 3. Now, in order to complete this standard form, I must solve for the constant a. Okay, I must solve for the constant a. And in order to do that, I can plug in my given point. I know that if I plug in 0 for x, I have to get out 2 for y. 2 is equal to a times the quantity 0 minus 2 squared plus 3. 0 minus 2, that's a -2 squared, would be 4a. If I subtract the 3 to the other side, that gives me -1 is equal to a times 4, which means that a is equal to -1/4. Now that we have solved for this constant, we can write our final equation. Remember, your final equation needs to have all the constants solved for, and you need to leave your variables x and y. Our final answer would be -1/4 times the quantity x minus 2 squared plus 3. All right, and now we could very easily sketch the graph of this parabola. Okay, we know that the vertex is located at 2, 3. We know it has to go through the point 0, 2, and because our a value is negative, we know that our parabola is going to open downward. All right, so here we have the graph. Vertex at 2, 3 goes through the point 0, 2, that's our y-intercept, and the graph is going to open down. We can easily get a quick sketch. All right. Find the x-intercepts of the following quadratic. Check your work using a graphing utility. So we've talked about finding x-intercepts before. Another word for x-intercepts is the zeros. And to find the zeros, we set y equal to 0. Set the equation equal to 0. 0 is equal to x squared minus 8x plus 16. Well, here we have a quadratic equation, and you guys already know to solve zeros of a quadratic equation, we need to think about factoring. All right, so what does this quadratic factor into? Well, we get 0 is equal to x minus 4 times x minus 4, which tells us what's our x-intercept? X is equal to 4. What does it mean if there is only one x-intercept? Well, if it only hits the x-axis in one place, then that must be the location of the vertex. All right, so you can take out your calculator and graph this function in your calculator. You will notice we end up with a parabola. It opens upward because the leading coefficient a is positive 1, and we have a vertex at 4, 0. Alrighty, let's try one more here. Find the x-intercepts of the following quadratic. Check your work using a graphing utility. We have f of x equals negative x squared minus 4x plus 1. Again, to find the zeros or x-intercepts of a quadratic, we set y equal to 0, and we want to think about factoring. Now, this guy right here is not going to factor, right? There are no factors of positive 1 that add to give me negative 4, all right? That's just not going to work out. And so if factoring is not an option, we can use the quadratic formula instead. The quadratic formula allows us to find zeros of quadratic equations. Okay, you guys might remember the quadratic formula from your previous algebra classes. X is equal to negative b plus or minus the square root of b squared minus 4ac all divided by 2a. In this case, to plug into the formula, right, remember this comes from the general form ax squared plus bx plus c. All right, a is going to be negative 1, b is going to be negative 4, and c is going to be positive 1 here in this equation. That gives us with a positive 4. Remember, we're subtracting that's negative 1 times negative 4 gives me a positive 4, plus or minus the square root of negative 4 squared is 16, plus 4, so plus 4, because we are taking negative 4 times a negative 1, that gives me a plus 4, times a positive 1, still going to be plus 4, all divided by 2 times a, 2 times negative 1 gives me negative 2. All right, so now we can begin to simplify this out. This gives me 4 plus or minus root 20, all divided by negative 2. All right, can we simplify any of this? Yes. Let's start with our radical right here. 20, do we have any factors of 20 that are perfect squares? Well, that would be 4 times 5, so this becomes 4 plus or minus 2 root 5 divided by negative 2. And now we can divide each term up top by negative 2, giving us our final answer of negative 2 plus or minus root 5. All right, those are the zeros and the x-intercepts of this particular quadratic using the quadratic formula. And if you were to plug in and get decimal approximations, that would be x is approximately negative 4.263 and positive 0.236. Sorry, negative 4.236 and positive 0.236. All right, so we could graph that in our calculators. And if you're using a TI-84, you can use the second calc 0 feature of your calculator to double check those decimal approximations. All right, make sure you know how to use the calc 0 feature. If you don't know how to use the calc 0 feature to calculate zeros on your calculator, make sure you ask. All right, so there is our introduction to quadratics. We'll talk a little bit more about quadratics in the next video.